first let's do what is convolution. Let's do a numerical example. 2, 0, let's do a little bigger. I'm pulling some numbers out of nowhere. 2, 0, 3, 1, 0, 1, 2. Those are numbers. Let's make a convolutional kernel. How about 1, 2, 3? Sound good? Okay. We could call that vector our image, and we could call this vector our filter if we wanted to. Haven't really defined those. I'm just saying, let's call them that. Actually, I'm going to call this one, how about input, and I'll call this one filter. And I'm going to apply my filter by doing dot product. So, what is 2 times 1 plus 0 times 2 plus 3 times 3? It's 2 plus 9 is 11, right? I claim that the dot product of the overlapping portions of these two vectors is 11. Anybody think otherwise? If you do, you're wrong, unless I am mistaken. Because 2 times 1 plus 0 times 2 plus 3 times 3. See, I'm just multiplying the overlapping portions and then add them together. 9 times 11, that's 11. Okay. So now to do the next part, I'm going to take my filter and slide it over a little bit. And basically, I'm going to always write my answer right here in the middle. And I get 0 times 1 is 0, plus 3 times 2 is 6, plus 3 times 1 is 3, 6 plus 3 is 9. And then I'm going to slide my filter over a little bit. And now 3 plus 2 plus 0. See why I stuck a couple zeros in there? It makes my life so much easier here. Okay, that's 5. Then I slide my filter over a little bit more. Almost done. 1 plus 3 is 5. Oh, I mean 4. Thank you. It's hard to teach, you know. Your mind is worrying about so many different things. Math is about the last thing on my mind. Finally, 0 plus 2 plus 6 is 8. Okay. I have just I've taken the input, I have run it through a convolution filter, or I've convolved it with that kernel. So sometimes a filter is called a kernel. I don't really like that terminology. I'm just going to keep calling it a filter because I like that a little better. Think of the input or the image as being passed through a filter to compute the following output, and there you go. Notice something interesting. The output is a different size than the input, right? And in fact, well, it just is. Can you suppose I were to generate an arbitrary input size vector and an arbitrary filter size? Can you tell me a math equation that would compute the output size? It's going to basically be output size is equal to input size minus, wait, what is it? Minus filter divided by 2 plus 1? No, that's not right.
Just on us, like this one example, it looks like input minus filter plus 1.
Just leave off all the end of the filter.
It's a plus 1. That's what it is. Okay. There you go. It's not combinatorial. Basically, in fact, the bigger my filter is, the smaller my output's going to be. You see that? If my filter were the exact same size as the input, I'm only going to get one number. If my filter were the same size as the input minus 1, I'm going to get 2 numbers. And if my filter is only one number, then I'm going to get It's basically going to scale the input. All right? This process is called convolution, which I'll write up where you can't even read it. There. Why is it called convolution? Because it's convoluted and confusing and weird. I don't know. Because it is. It's called convolution. I don't know why. Now, now that we can do it, well, let's point out something. Well, let's get into the motivation now. Why should we do convolution? So it turns out that in the field of image processing, convolution is a really common operation to perform. There are some very common convolutional filters that will do things like edge detection or, darn it, that's the only one I know. Anyone taking image processing? What else can convolution do? Yeah, you can blur with convolution. I think you can even sharpen with convolution. You can do lots of, it turns out that a whole lot of image processing operations can be reduced to a convolutional filter. Oh, you can do a low pass filter, a high pass filter. There's a lot of things you can do to an image that involve convolution. And therefore, somebody was sitting around thinking, convolution, neural nets. What happens if we put the two together? And they did it, and wow, it worked really well. That person happens to be Yen LeCun, I don't even know how to say it. Or his grad student. I don't know who really came up with it first, but they published a paper on it, and basically the whole world ignored that paper for about 20 years. And suddenly 20 years later, it's probably more like 10 years later, I don't know how long it was, somebody else dug it up and said, hey, that's a cool thing to do with neural nets. And they built a convolutional neural network. And now that machines were finally fast and we finally had GPUs and we could do awesome things with it, they threw it at some really hard image recognition problems, and it beat the pants off of everything. And by everything, I don't just mean neural networks, which were beating a lot of image processing techniques. They beat everything. All the things the image processing people were doing, convolutional neural networks just suddenly came out of nowhere and surged ahead of image recognition, and they were winning benchmarks and beating a whole bunch of competitions, winning competitions, beating benchmarks, and people started to realize, oh my goodness, convolution's a really great operation for using on images. So suffice it to say, if this is your neural network and the input is an image, now the input is not always an image. Sometimes you have random things like the prices of homes in Boston and the value of your mom's shoes or whatever it is that you're feeding as input. And in those cases, convolution does not work very well. But when you have images as input, convolutional layers are really good at digesting images and making sense out of them and using them to predict what's in it. So in the case of the MNIST data set with which you're all familiar, we were looking at images and predicting digits, right? So you got like 300 errors on MNIST, 350 errors, right? We're going to implement convolutional layers, which by the way are just another layer in a neural network. And it turns out that you can stack layers of anything in a neural net. They don't have to be, we did linear layers and we did nonlinear layers. That pretty much covers everything, right? Kinda, because convolution's a nonlinear layer, but it's a nonlinear layer with weights. Point is, convolution is one of many things you can stick in as a layer in a neural network. You can stick in any type of math that's differentiable, and it will work. And convolution turns out to work really well with images. If you implement the topology that I give you somewhere in that assignment, you can get under 60 errors. I actually got 49 errors with that topology on MNIST. It took 3 days to train on one CPU working in serial, no GPU. Nobody really does that anymore. These days, everyone's throwing their neural networks at GPUs. Easiest way to do that is use some package that already interfaces with your GPU, like TensorFlow or something like that. But this class is about how does it all work. So we're going to learn how to implement a convolutional layer. Yes, yours is going to be slow. I don't care. but it should be able to do amazing things with images, and then you'll really be the masters of how to use TensorFlow and things like that. Okay. Finally, before I close, before I hand back your test, we did convolution with a 1D vector. How do you do convolution with a 2D image? Suppose this is your image, and this square represents your filter, and this is a great big field of pixel values. Now how do we do convolution? Well, take this filter and you lay it over part of the image, and let's say there are 9 overlapping pixels. So we could call them P1, P2, P3, P4, P5, P6, P7, P8, and P9, right? Well, in each of those 9 spots, you've also got filter 1 through filter 9. You could multiply all the overlapping parts together, sum them up, and it's almost the same thing we just did, right? Well, there you go. That's convolution in 2D. So we'll take our filter and we'll kind of slide it over all this image, and we'll visit every location in the whole image, and as soon as we've rastered across the whole thing, the output will be another image, which will be slightly smaller than that image, depending on the width of your filter. And so basically convolution takes this image and produces that image. And this is the input image, and that's the output image. So if you had 5 layers of convolutional, if you had 5 convolutional layers, you would map from this image to that image to the next image to the next image until eventually you have an image that's a little smaller. And then you could take all those pixels and feed them into a linear layer like we did in the MNIST assignment. Was that assignment 2? And then you could predict what digit you were looking at, and then it would make good predictions. Yeah.
So, whereas normally we'd have like every unit in a layer connected to every unit in the next layer, we're only going to have as many connections as there are on the filter.
That's right. So the number of weights in a convolutional layer is actually pretty darn small. It's actually the size of your filter. And this is the number of, so imagine, if you will, this is a 1024 by 768 pixel image, because that's a common size image, isn't it? Or it was, back in the days of crappy resolution. And so 1024 times 768 means there are 786,432 pixels in this image. And there are 3 color channels per pixel if we do it in color, because life isn't black and white, right? And if we connect a layer with that many units to another layer with a similar, comparable number of units, we end up with 5.5 times 10 to the 12th power number of weights in that one layer alone. Do you see that that's going to take basically all of eternity to train? Turns out convolution is a subset of fully connected. A convolutional layer can do nothing that a fully connected layer can't do, given all of eternity and a Turing machine. But in a reasonable amount of time with a real machine, convolution still seems to work because it has a very, very limited number of weights. And that is really the main thing about it. So why is convolution so awesome? Because it limits the number of weights and still doesn't stink. So it's not that convolution is better or more powerful than a fully connected layer. It's not. It's that it's less powerful in ways that we don't care about. And that's what convolution's awesome for. I'm going to return the test now. We'll talk more about convolution later, and most importantly, how to differentiate it, because that's what you need to implement it in a neural network. But for right now, I'm going to spread out your tests and hand them back. So I guess that's the end.